Bismillah ar-Rahman ar-Rahim. Today we are going to discuss the last functional block, okay, which is called the demultiplexer. Okay, basically a demultiplexer performs the inverse operation of a multiplexer. So just to remind you about multiplexer, it's a circuit that takes what? That takes n inputs, for example, or 2 to n inputs, and produces one output. All right, and you can select one of the 2 to n inputs using a selection line that is n-bit wide. Okay, the demultiplexer is the other way around. You have a one input. Okay, here it's called I here. And notice, by the way, notice the difference between the multiplexer and demultiplexer. The demultiplexer expands this way, and the multiplexer expands the other way. Okay, so it expands as we go to the inputs. Okay, so it's the opposite, exactly the opposite of the Dmux is even graphically it's opposite. So do not confuse the symbol for the mux and Dmux. Okay, so we have one input here and 2 to n outputs. Okay, the 0 up to 2 to n minus 1. All right, so in total we have 2 to the n outputs, and to select to route the input to one of the 2 to the n output, we need n bit for that. Okay, this is the n bit selection line. Okay, so the basically the function of the demultiplexer is that it directs I or connects I to one of the 2 to n outputs based on S, the value of S. So basically D sub S will be I, and D sub J will be 0 for any J that does not equal to S. Okay? Okay, now so a demultiplexer with 2 to n outputs is called 1 to 2 to n Dmux. Okay, 1 to 2 to n Dmux. And you can implement the demultiplexer now. We have given you enough training to implement it yourself. However, using basically truth table and then K-map. However, you must observe that a demultiplexer can also be implemented using a decoder with enable. Okay, so this is a demultiplexer here. All right, it has a single input I, and let's say we want to discuss, be concrete here. Okay, we have a 1 to 4 demultiplexer, which has 2 selection lines, S1 and S0, and 4 output lines. All right, this can be represented using a 2 to 4 decoder with enable, in which we connect enable input to I and A1 to S1 and A0 to S0. Then the outputs will be the same. Okay, so this is equivalent to this exactly. So if I ask you now, can we use demultiplexers to implement arbitrary Boolean functions? Your answer should be
yes, because they involve decoders.
Yeah, so we can do that with decoders. So we can do it with demultiplexers, of course. Yeah.
Doctor.
Yes.
I don't know why. What does enable do here exactly? Why can't it be just a 2 to 4 decoder? It would be the same as Dmux, right?
Yeah. What if your I is 0 here? What happens if your I is 0? Forget about this now. Forget about this. What if your I is 0 here?
I will be forwarding I to whatever these based
no,
on
no, regardless of forwarding, okay, it will be all zeros. You immediately say, without even knowing what is S, it will be all zeros.
If I zeros, I don't have to do any selection.
No. It does a selection, but I'm asking you because you know the functionality of the demultiplexer, okay? So the functionality of the demultiplexer, what does it do? As I told you, D sub S will be equal to I. And D sub J for any J that does not equal to S is 0. So if I is 0, then all the outputs will be 0. See that?
Yes, I see.
Yeah. So in this case, your I is nothing but the enable input of the decoder. So if enable is 0, remember, if enable is 0, then the decoder will have 0 outputs, all. But if enable is 1, then it will, you can think of it as forwarding this one to one of the outputs. Okay, it's exactly the same functionality as the demultiplexer. Okay, all right.
Yes, clear.
So I just said that here. Okay, all right. Let's now discuss some design examples. Okay, this is the fun part of this chapter. Okay, and here we are trying to implement what we call a 2x2 crossbar switch. Okay, and the functionality here is shown by this if statement here. So you have a black box like this one here. It takes M bit A and M bit B and produces two outputs, M bit X and Y, and it has a selection, okay, or an input S, not a selection, basically it's an input S that is 1 bit, okay, and its functionality should be like this in this if statement. If S is 0, then my X will be A and my Y will be B. Else it is the other way around. My X will be B and my Y will be A. Okay, so basically when my S is 0, you can think of the connection like this, exactly. Okay, and when my S is 1, I'm going to cross them like this. Okay, so this is why it's called the crossbar switch. Okay, it's a 2x2 crossbar switch. Now, how do you implement that? You have many ways to implement it. You can implement it in many ways. Okay, even using Boolean algebra, but I mean not Boolean, I mean K-map, but because we have M-bit, it's very almost impossible to deal with K-maps, and your K-map size will be too much. All right, but we can do it using high-level thinking, and I told you that when you have if statements, you should think immediately about multiplexers. Okay, so first of all, let's create a multiplexer that we can split this if statement into two if statements. Okay, one for X and one for Y, right? So we can say, well, this can be split into if S is 0, then X is A, else X is B, right? And another if statement. So I can implement this using a multiplexer, right? So there is my multiplexer, M bit 2 to 1 multiplexer. So this is input number 0 and this is input number 1. Okay. And I can say max here just to indicate that. All right. And there is my single bit selection line, which is basically S. It's the same S as the problem. Okay. And here I have A, because when S is 0, my X should get A, right? When S is 0, this S here is 0, I should get A. And when S is 1, I should get B. And both of these are M-bit. And I just forgot to write the so this is n minus 1 to 0, and this is n, because I need to emphasize that this is not just a single bit, it's a vector, okay? It's a vector, and the output here is what? Who can tell me what is the output? Come on, guys, this is a simple question. It's not a tricky question. Read the if statement and you'll figure it out immediately. What are we trying to calculate here?
Choose one of them.
Yeah, but what do we call the output? What is the name of the output?
X or A, I mean A or B.
It's X, basically X, okay? It's X. So this is X. So X takes A one time and takes B one time, depending on the value of X, depending on the value of S. Okay, so it's X, n minus 1 to 0. And this is also n bit, okay? Now this is for X. For Y, it's similar. So if S is 0, then Y is B now. Else Y is A, right? So we can draw the same multiplexer here. But the output will be, instead of X, it is Y. And we have to, who can tell me what's the change that we need to do in order to make this correct for Y?
We should swap the 1 and the 0.
Excellent.
Make
This is
S
one
complement.
choice. This is one choice. Yeah, you can either do this. This is 1 and this is 0. You say, okay, or who can tell me another option?
Or complement S.
Excellent. Yeah. So you say, well, this is S complement instead of S. Okay. So you can see that the solution here is using the switching instead of S complement. Okay. Switching instead of S complement. Here for the Y, you can see that the A is going to input number 1 and the B is going to input number 0. Okay. And for the X, it's the other way around. But you could have used also an inverter and route them to the same input lines. Okay. So more than one. Maybe you'll if you think about this yourself, without seeing the solution here, maybe you'll come up with a different solution. So this is the beauty of MSI design. Okay, it's always open-ended design questions. Okay, you can think of, for example, it's similar to programming. Okay, you can write a program in many ways. Okay, some ways are more efficient than others, but in general, okay, they all do the same thing. Okay, maybe we will sometime in the exams. Okay, we tell you, we constrain the problem. Maybe we say you cannot use more than one adder, for example, only one adder for the whole thing. Okay, or you cannot use more than one decoder or something like that. Okay. Then you have to respect that constraint and think within or inside the box. But if you are not given any constraint, then you can come up with any solution. Okay. Is the problem and the solution clear? Because we are going to move on to next problem now.
Doctor.
Yes.
You could just switch the inputs to the other multiplexer, right?
Come again?
So input for the other multiplexer, you asked what do you need to change. We can input B to 0 and A to 1 instead of changing them.
Instead of complementing S, you mean?
Yes.
Yeah, this is what is done in the solution. Yes, you're right. This is you can see that B here is at 1 for X and it is at 0 for Y.
If they were inputted at the same first multiplexer, it would give me a duplicate, right? If I routed them the same way as the first multiplexer.
You cannot use one multiplexer for both. You cannot. These are two different outputs. Okay?
Yes.
You just cannot use one multiplexer for both. These are two different outputs, you can see. Okay? And they behave differently. So in this case, you have to use two multiplexers. Okay? Not just one.
Yes.
Okay, let's move on to another problem. It's a problem of sorting two unsigned integers. Okay, and this is fun. Okay, so you have two integers, a and b. Okay, both are m-bit. Okay, and we would like to calculate the outputs, which are x and y, where x is the minimum of a and b, and y is the maximum of a and b. So it's some sort of or a kind of a sorting problem. Okay. All right. So we can use what we have done before. Okay, using the crossbar. Okay, but then for S we can control it using a comparator. Okay, a comparator. So here, so remember, we are picking an order of A and B. It's either A, B, or B, A. Okay, so the output is exactly what we are looking for here. Okay, it's either A, B, or B, A. So in order to produce the correct output for the sorter, I just need to control the S in a way to help me implement the sorter. Okay, so if I connect the select line of the multiplexers to A greater than B of the m-bit magnitude comparator, and I feed A and B to the magnitude comparator, then what happens? If A is greater than B, if this is true, okay, if this is true, then this is 1, right? And if this is 1, I'm going to output B here because it's the minimum, X gets the minimum, okay? Because A is greater than B. Remember, A is greater than B. And for the second one, we get A, which is the maximum. If A is not greater than B, on the other hand, so this is 0 now. A is not greater than B, so B is the maximum. Okay, B is the maximum. So this is 0 now. Then we output here A, which is the minimum, in fact, and B for the other one, B. Okay, and what is B here? Okay, this is 0. Okay, which is the maximum. You get it? Any question here?
For A larger than B, yes, but for A equal B, tool output.
No, for A equal B, whatever the order is fine. But they are both the same here. It doesn't matter because they are equal. Remember?
Yes.
So it's the only case we care about is when A is greater than B or not greater than B. If it is equal, then whatever the output, whatever you put here, A or B, or here A or B, they'll be the same. Okay, any other question here? Okay, no questions are there. I'm going to move to the next level. Okay. Now we talk about arithmetic and logic unit. Okay. So we have here, this is the shape of an ALU. Okay, so it's usually the ALU is a major component in a CPU. Okay, when we design CPUs in for example COE, the course COE 301, which is the computer organization course, we use this symbol for the ALU. Okay, and ALU is central in computer architecture. It's one of the major components, and designing the ALU efficiently is an objective. It's a major objective in the design process. One of the things that you really need to do when designing an ALU is to share the components, especially adders. When you do some kind of addition and subtraction, you need to do it using one component. Okay, one adder for all. Okay, because usually adders are very expensive. Okay, and usually we don't use what we call ripple carry adders that we have seen in the previous unit. Okay, but we use something called carry lockerhead adder, or even more sophisticated version than that. Okay, a carry lockerhead adder is very expensive. Okay, it consists of many more gates than the ripple carry adder, but it's very fast. Okay. So having one carry lockerhead adder, for example, in the ALU is fine, but if you duplicate it, the ALU size will boom. Okay, it will grow very much. Okay, so we usually when we ask you an ALU question, we usually say do not use more than one adder in this unit. Okay, so here we have a function. Okay, a function selector, which is shown to be 3-bit here. Okay, and we have operands A and B, which are n-bit. All right, and the output, which is n-bit as well, R. Okay, and we have also a carry out as a bit, and overflow as a bit. Okay, and the functions for the ALU, okay, depends on the if function field. Okay, usually this comes from when we discuss computer organization. This is coming from decoding an instruction. Okay, instruction is, for example, if the instruction is add, then this will translate to add, which is 000. Okay, if the instruction is subtract, then this will translate to 010. Okay, actually no, it's 011. This is subtract. This is subtract minus 1. Okay, all right. So what are the functions in this ALU, specific ALU that we want to design? We have 3-bit for the function, so we expect to have 8 functions. Okay, because 3-bit 2 to the 3 is 8, right? So this is the function table, and you can see here that if the most significant bit of the function, okay, is 0 here for arithmetic operations, and it's 1 for logic operations. So it makes sense that we will have a branch of the ALU to calculate the logic results, and then another path to calculate the arithmetic results, and then have a one multiplexer, n-bit multiplexer, to choose whether we are doing the arithmetic or logic path using, and what do we use for selection? We use the most significant bit of f. Okay, either 0 or 1. Okay, okay. Now for the arithmetic, part. Okay, I'm going to write it down here below in order to illustrate it to you. So we have F2, F1, F0.
Hey, doctor.
Yes.
Sorry, but we are going to need to use 2 multiplexers, right? One for the most significant, and then for the other operation. So if it is a Boolean or arithmetic, and then choosing from Boolean or choosing from arithmetic.
Yeah, we have 8 functions basically. Yes.
No, I'm saying we need to use more than one multiplexer, right?
Yes, yes, of course. But I just hinted you that you have 2 paths. Okay, so the final result will be one of the 2. So you have to have one, at least a final multiplexer. But in fact, you're right. We'll be using more than one multiplexer. Okay, yeah, you're definitely right. So this is my R now. This is the function table. Okay, so I have 0, 1, 0, 1. So I'm just concentrating on the top part of the table now. 0, 0, 1, 1, and then all zeros, which is the arithmetic part. Now this one here is going to be A plus B, right? And this one here is going to be A plus B plus 1, right? And this one is A minus B minus 1, and this one is going to be A minus B. What do we do with these? You remember we are doing operations in 2's complement, right? So we have to translate that into 2's complement. So this equals, this is my my new R now, A plus B, okay, is nothing but A plus B, okay? But assuming that A and B are, yeah.
2's complement 4.
Yeah, they are. We can assume that. Yeah, fine. Yeah. So A plus B, and then A plus B plus 1 is A plus B and plus 1. That's a carry in, right? And here the carry in, just for consistency, we just add 0 here. Okay. And here, for this one, we can work it out here, somewhere here. So it's A minus B minus 1, okay? And that in 2's complement, what it is? A plus
B complement.
B complement plus 1, right? And then minus 1,
Yes.
right? We have a minus 1 here.
Cancel out.
So these cancel out, and the result will be A plus B complement. Yeah, so A plus B complement plus 0, right? Which is the carry in now. So I'm just preparing the operands for the adder now. Okay? And then this one here is going to be A plus B complement plus 1. You can see that the carry in is this one here. Oops, sorry. The carry in here is 0, 1, 0, 1 for these values of f. Okay? And B will be either B, B, B complement, B complement, depending on the value of F1 here. Okay? And A is always A, regardless of any function. Okay? So we expect that A is the same. A is always A in the arithmetic part. Okay? So if you think about your adder now, think about your adder. You have a ripple carry adder, 4-bit ripple carry adder, actually n-bit ripple carry adder, because A and B are n-bit, ripple carry adder. And you have A here and B here, and you have your carry in. Who can tell me what is the carry in now?
It will be 0 if 0 is 0.
Okay. And
1 if 0 is 1.
so
we need the selection for that.
no selection, it's just F0.
Oh, yes, yes, F0 actually. Yes, I just noticed that. Yes.
F0. Just try to be, I mean,
yes, yes.
Yeah, you don't need a selection here, okay? Here it's A, okay? This is n-bit, all right? And here it is either B or B complement, right? Now you need a multiplexer here.
Yes, now we use it here.
Yeah. So the multiplexer will be controlled by F1. You can see that, right? So we have a 2-to-1 multiplexer here. Forgive my drawing skills. And this is 0 and this is 1. And this is my selection line, which is connected to F1, right? In case F1 is 0, I get
B.
And in case it is 1, I
B
get
complement.
B complement. Yeah. So now we finished the arithmetic part, okay? But still, we are not done, okay? What is, by the way, what is the, so we assume that our ripple carry adder will also produce for us the V and
The sum and the carry.
the C out, okay, which is C in this case, it's C.
The V.
Yeah, and the V, okay, and also the V, which is C out XORed with the previous carry out, okay.
Yes, C out XOR C out minus 1.
Yes. So so this is in bit here, okay, and it's not our final R. No, not yet. Because why? Because maybe the function is logical, not arithmetic. Okay. So for logical, it's simple. Okay. So for logical, we have 4-to-1 multiplexer. Okay, 4-to-1 multiplexer, and we have 0, 1, 2, and 3. And the selection is going to be what? Based on F1 and F0. F1 and F0, yes. F1. So this is S1 and S0. So this is going to be hooked up to F1. And this is going to be hooked up to F0. And for 0, we get what? For 0, we get A and B. This is in bit, okay? A, which is in bit, and B, which is in bit. Okay, so we assume this is well, you can use this, by the way. It means that we have n and gate when we are ending the bits bitwise. Okay, so A0 ended with B0, A1 ended with A1, and so with B1. I'm sorry, yeah, and so on and so forth until the end. So this means that we have an n, a bank of n and gates. Okay, the next one is going to be A or B. Not like this. 4 A, B. And the next one is going to be not A or B. So we take, this is 4, okay? Actually, we take an inverter here and feed it here. Okay, 4. Right, the final one is A XOR B. So A and B. This is 4, this is 4. And finally, we get our output. Actually, I'm saying 4, and you should have told
Dr.
me that this is in.
Yes, I was just saying, even in the ripple carry, should all be ends.
Yeah, in the ripple carry. Oh,
the ripple carry also, yes, in the demultiplexer.
So anyway, whenever I'm not going to change it here, just pay attention to what I say. 4 means in here, okay?
Yes.
In, okay, and so on and so forth. Okay. Anyway, you'll get it in the next slide anyway. Okay. So we have here the output is going to be n, and finally you have a multiplexer, an n bit multiplexer, 2-to-1, 1. That will produce your R. Okay, R what? R n minus 1 to 0. Okay, and I didn't do it for A and B, but you know that this is there. Okay, this is n, all right, and we take we connect this to 0 and this to 1, and the selection here is
F2.
F2. Excellent.
But doctor,
Yes.
isn't this multiplexer should be at the beginning? Why do the operations and then choose between them? Isn't this like
You have to do the operation because this is combinational logic. It's not like sequential logic. It's not.
I mean, can't we move the multiplexer in the beginning and choose
No.
based
Even
on
if you do
F2?
that, okay, even if you can do that, let's suppose that you can do that. This operation here is going to execute no matter what. Okay, unless you cut the power supply from this path. Okay, so
Yes.
because it's connected to the input, it has to be executed. But I suspect that you can do it at the beginning. No. But
Yeah, I know it's weird design, but
come again.
I know it's weird design, but I just thought about it. We are
No,
doing
you
both
can,
and
you
then
can
choose.
actually, you can do it. You can also have the adder. Okay. I don't know. Maybe there is another design, but it's not going to be neater than this.
Yes,
Okay.
I see. This is optimal.
So this is no, it's not necessarily optimal, but it's acceptable. Okay. So you can see here that he is doing this in order to create the overflow, assuming that he has access to Cn minus 1 and Cn. Okay, so you can create the overflow signal by just XORing the two, and the final carry out is C. Okay, and this is nothing but what we did. Okay, except that he's not using a multiplexer here, but he's using an XOR gate. Okay, instead of a multiplexer, and you should also see that an XOR gate is nothing but. So if you think about the XOR gate, for example, if I tell you that this is X and this is S, okay? So yeah, if you think about this, then this is equivalent to multiplexer, one that takes X here, an X complement, and chooses based on S. Okay, and when S is 0 here, okay, you'll get X, and when S was 1, you'll get X complement. You see that? So similarly here, when S is 0,
using XOR would be more efficient, right? Faster.
Yeah, actually, it's almost the same because XOR is a compound gate. It's not a simple gate. Okay.
Yes.
So the XOR is going to be implemented using, if you calculate it, okay, you calculate it, you'll see that because it's going to be X ANDed with S complement, okay, or with S and X complement, yeah.
Yes.
So when S is 0, you'll choose X, and when S is 1, you'll choose X complement. Okay, it's exactly the same functionality as this one. So it's the same, effectively the same. Okay, but using XOR sometimes is easier than drawing the symbol of the multiplexer. Okay. All right. Any other question here? Okay, let's move on. This is an exam question. Okay, and we are requesting to basically implement this ALU. All right. And for this, I need to, again, write it in a consistent way. So this is going to be A plus B plus 0, because I'm going to use one adder for that. Okay. And A plus B complement plus 1. And then we have B minus A. So it's going to be what? B minus A is B
B
plus
plus A complement plus 1.
plus 1, right? So I can reorder that to be A complement, okay, plus B, and this is a bad B, plus 1, yeah? And then minus A minus B minus 1. So it's A complement plus 1 plus B complement plus 1 minus 1. So these cancels, and then you're left with A complement plus B complement plus 1, right? And you can do that easily here, okay? First of all, you can do it with XOR gates, by the way. You can do it quickly here if you want. So S1 will control the inversion of A. So we have A and then S1. Yeah, I'm not going to write the widths right now because we need to hurry up here. So, and the question, by the way, says ignore overflow. So you don't need to extend, okay? 4-bit. Is it 4? Yeah, 4-bit. RCA. Or adder, you can say 4-bit adder, all right? Binary adder. And we have a carry in here, which is what? Which is basically S1 ORed with S0, right? It's 0, 1, 1, 1. So it's the OR of them, okay?
Yes.
And for B, this is A. And for B, we have S0 to control the inversion here. So this is B, and this is S0. But notice that, okay, I have to do that probably. This is 4, and this is just 1. We don't write the 1, okay? And this is 4, okay? So the output here is 4. So we assume that this bit is XORed with all of them. So it's extended. Okay, I can write it in a better way here. I can say S1, 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 S1. Okay, and then this is 4. So and then similarly for this one here, it's just to be consistent, S0, 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 S0. All right, and then this is 4. All right, and this is 4. And the result is going to be my C, right? You see that? This is not a bubble, by the way. It's just an OR gate, normal OR gate.
We'd have a C out also, right?
We don't need that. Don't need that in the yeah, but you can just write it down here, but you don't need it for the calculation. Remember, when you do 2's complement addition and subtraction, you ignore
Yes, you ignore
the carry out. Yeah. So your C is composed of yeah, is 4-bit. That's it. Okay, this is about this question. Okay, what about this is also another exam question. Okay, I think we don't have time to do this, but really quickly. Okay, really quickly. What's the so we would like to we did this before, I think. Yeah. Basically, this is a mapping between. So you have a 3 to 8 decoder because you have 3 inputs. Then you generate 8 minterms, and then you connect that to an encoder, okay, to generate these 3 outputs wise. Okay, so if your input is 0, 0, 0, then you connect D0 to where? To the second or D2 of the encoder, okay, in order to get this value at the output. So you have the decoder here, okay. So if you have so this is let's call it A2, A1, A0, all right, and the most significant bit here is X2, x1, x0. All right. And here we have D0. Actually, let me just try
Doctor,
to.
are we just implementing the min terms of this truth table since we're going to use a decoder?
Yeah, I mean.
So, and because I'm not getting the
No,
idea of
no,
the
no,
question.
no, no. It's
I'm not following.
it's basically the thing is that. Oh, okay. So this is a different question here. I see. Yes. So you are right. You're right. So what is y2 now? Y2 is x2 basically. You don't need even a decoder for that, right? This is y2, right? Yeah. And what is y1?
Yes.
Y1 is going to be 0, 0, min term number 0, or with min term number?
Number 1.
Yeah. I'm sorry, I confused this question with another question that is coming up, okay? And y0 is the NOR of...
you can say max terms, max term number 0, max term number 1.
Yeah, so basically it's...
Oh, no, sorry. Yes, you did the NOR. Just take the other indices.
This is y, this is y1, basically, and this is y0, okay? Okay. Yeah. So yeah, this is one solution. The other solution, notice that you can do this with, this is a 3 to 8 decoder, okay? But you can do this, just think a little bit, and notice that you can do this with 2 to 4 decoder instead of just 3 to 8 decoder, okay? Okay, I'm going to stop here, and we will continue, inshallah, next time by discussing these also exam questions, okay? So don't miss them, okay? I'll see you next time. We have a question.
Yes, sorry, but can you open the attendance? I missed it.
Yes, me too.
Let me stop recording.